This is Module 1, Use of Manipulatives and Strategies with a focus on decimals. This is Part 2 of a 3-part professional learning session for Module 1. We encourage you to follow along and construct the visual representations discussed within this session. Feel free to pause the presentation at any point. For the examples using base 10 blocks, the flat will represent one whole. The rod represents 1/10 because it is one of 10 parts needed to create a whole, and the unit represents 100. It is one of 100 parts needed to create one whole. As with most other manipulatives, base 10 blocks can be used flexibly. Each block only needs a label to identify what it is representing. To represent 1 and 54/100ths, we have used a flat, 5 rods, and 4 units, 1 whole, 5/10ths, and 4/100ths. 33/100ths is represented with 3 rods and 3 units, which is 3/10ths and 3/100ths. Like blocks are combined, flats with flats, rods with rods, and units with units, or wholes, tenths, and hundredths. Think about this. How could you use this same strategy to solve 1 and 54/100ths minus 33/100ths? Place value charts may prove a useful tool for students who have difficulty identifying the place of a digit. Here we have inserted each digit from both add-ins into the place value chart. This allows us to see how many ones, tenths, and hundredths we are adding. We have 1 whole, 8/10ths, and 7/100ths. In standard form, it is 1 and 87/100ths. Empty number lines differ from traditional number lines as they do not contain hash marks nor equal intervals. They are very flexible and can be manipulated to best meet the needs of the student employing the number line. Here, beginning with the greater quantity, we have used the empty number line to solve the problem. The second add-in was broken into place value parts. Notice the jump sizes vary depending upon the amount jumped. Starting with 1 and 54/100ths, we added 3/100ths and noted where that amount has moved us on the number line. With 3/10ths left to add, the new amount is increased by 3/10ths, and the final location is represented on the number line. 1 and 54/100ths plus 33/100ths is the same as 1 and 87/100ths. With the following examples, the flat represents a whole, the rod represents a tenth, and the unit represents 100th. Using base 10 blocks, we can create an area model using concrete materials. The length of this rectangle is 1 and 4/10ths, represented by 1 flat and 4 rods. The width of the rectangle is 4/10ths, represented by 4 rods. We want to determine the area of this rectangle. One part of the area is determined when 1 is multiplied by 4/10ths, which is equivalent to 4/10ths. The next part of the area is found by multiplying 4/10ths by 4/10ths, which is 16/100ths. The benefits of using concrete materials to find the area is students are able to use the size of the area to determine which block to use. With ample experiences, students can derive multiplying a tenth by a tenth most likely will result in hundredths, and multiplying wholes by tenths will most likely result in tenths. To determine the area, combine the partial areas of 4/10 and 16/100. Students can even exchange 10/100 for 1/10. Either strategy will result in the product of 56/100.
Think about this. What is the length of this rectangle? What is the width of this rectangle? And how do you know?
Base 10 fractions are also referred to as decimal fractions. They are distinguished by their denominators, which are 10, 100, 1000, and so on.
Decimals and fraction both are parts of a whole. When students and teachers use proper mathematical language when referring to decimals, the connection to base 10 fractions is clear. In this example, 1 and 4/10 is converted to a mixed number. 1 is the whole within the decimal and the mixed number. As a decimal, 4 is in the tens place, denoting it is out of 10 equal parts. This is why we have written it as 4 over 10 or 4/10 as a fraction. Here we are showing the mixed number being converted to an improper fraction. This step is not required, as students can apply a partial product strategy here. Multiplying numerator and numerator, as well as denominator and denominator, we arrive at the product of 56 over 100. 56 over 100, or 56 hundredths, can be converted to a decimal answer.
Think about this. Can this strategy be used with numbers containing 3 or 4 decimal places?
The partial product strategy we discussed in part 1 of this three-part session can be applied to other types of numbers. Using partial products, we multiply the wholes by the other's tenths, then tenths by tenths. The partial products are combined to find the product of 1 and 4/10 times 4/10. Keeping our thinking flexible, we will explore using base 10 materials to visually represent the division of decimals and how base 10 fractions help bridge the gap between fractional understanding and decimals. This rectangle has an area of 2 and 31/100 square units, composed of 2 wholes, 3/10, and 1/100. The length of the rectangle is 2 and 1/10. The red line highlights the length. Notice going across is 2 wholes and 1/10. We must determine the width of this rectangle. Taking a closer look at the width, it is composed of 1 whole and 1/10. The width of the rectangle is 1 and 1/10. Therefore, 2 and 31/100 divided by 2 and 1/10 is 1 and 1/10.
Think about this. How does this strategy relate to using base 10 blocks for multiplication?
Here we're using the same strategy with a written representation. The area is 3 and 6/10, and the width is 1 and 2/10. The rectangle now displays the wholes and tenths within the area. Take a look at the width of the rectangle. Notice it is 3 wholes going down. The width is 3. 3 and 6 tenths divided by 1 and 2 tenths is 3.
Think about this. Why is it important to have more than one strategy?
As the decimals within the equation become less friendly, students will need to apply a more efficient strategy. Just as when we were applying the base 10 fractions with multiplication, we have converted the decimals to mixed numbers and fractions. Here we are using the common denominator strategy as discussed in part 1 of this 3-part session. We have decided to convert the mixed number to an improper fraction. Because we are dealing with the same size pieces, we are looking to find how many groups of 20 are in 136. Many believe the standard algorithm is the most efficient strategy for dividing decimals. We want to reiterate one very foundational idea with using the standard algorithm. Remember, the mathematical language we use can create misconceptions or alleviate them. One misconception many educators have, so in turn students have, is the movement of the decimal point. 4 MBT1 states students should be able to recognize that in a multi-digit whole number, a digit in one place represents 10 times what it represents in the place to its right. And in 5 MBT1, it says students should recognize that in a multi-digit number, a digit in one place represents 10 times as much as it represents in the place to its right, and 1/10 of what it represents in the place to its left. If students are developing this understanding in 4th and 5th grade, it isn't a hard leap to make the place value connection with this algorithm. Here we have equivalent expressions. The dividend and the divisor have both been multiplied by 10. So the 2 in 2 and 6 tenths actually shifts to the tens place. And the 4 in 4 and 83 hundredths has shifted to the tens place. The decimal point remained between the ones and the tenths places.
What do you do when students struggle? Allowing students to work at their own pace to build their understanding will be helpful. It is okay for students to remain in the representational stage of this three-stage process of thinking.
Tiered tasks are a great way to allow students to work at their own pace of understanding while continuing to move through the curriculum. You may have a single task tiered at 3 different levels: below expectation, at expectation, and above expectation. Here's an example of a tiered task. The order of the tiers does not matter. We have aligned Tier 1 to above expectation, where students will work with larger numbers. Tier 2 presents smaller quantities, but still requires students to use abstract reasoning to support their answers. Tier 3 only requires the use of representations, whether concrete or visual. Small group instruction is not just a quote unquote elementary thing, it benefits all learners at all levels. We have pulled some suggestions from a global math department session.
Meeting with small groups of students is certainly beneficial. We have pulled suggestions for implementing small groups. The link listed will provide insight on how other teachers are implementing small groups at the secondary level.
This suggestion comes from the Social Emotional Learning and Mathematics session from Global Math Department. It lists a class size of 30 students to demonstrate you do not have to have a small class size in order to implement small group instruction. The Georgia Department of Education is not suggesting the foundations of algebra class sizes should be increased to 30 students. This suggestion comes from the Social Emotional Learning and Mathematics session from Global Math Department. It lists a class size of 30 students to demonstrate you do not have to have a small class size in order to implement small group instruction. The Georgia Department of Education is not suggesting the foundations of algebra class sizes should be increased to 30 students.
The Georgia DOE has created a wiki space for high school teachers to engage in discussions about math teaching with the Georgia Standards of Excellence. Here you'll find a forum to keep the conversation going, resources, and you may even make a few friends. It's a call to action and you are invited to make a difference. Access the online community here at ccgpsmathematics9-10.wikispaces.com.